In this chapter, we're going to be discussing temperature, heat, and expansion. All right, first of all, temperature. Well, we're familiar with temperature. It's in terms of sensing how hot or cold something is. You put your hand on a warm stove, you can sense that the temperature might be fairly high. You dip your hands in ice water, you can feel that it's much colder. Well, a more formal definition of temperature is the average kinetic energy of the molecules. And we learned before that kinetic energy is energy of motion. So when something is at a higher temperature, it tells us that the kinetic energy of the molecules are higher, which means that the molecules are in motion at a faster rate. Now, there are several scales for measuring temperature. You might be familiar with Fahrenheit, I'm sure. A more common one that's used in chemistry and physics is the Celsius scale. And the Celsius scale, the 0 point is based on the freezing point of water, and 100 degrees Celsius is the boiling point of water. Another scale is the Kelvin scale. This one is very useful because it has not an arbitrary zero like these two scales, but an absolute zero. In other words, when it's 0 on the Kelvin scale, that means that the kinetic energy of the molecules are 0, which means the molecules are not moving. We'll talk a little bit more about that one later. Okay, now a related concept is heat. And heat is energy that flows between objects of different temperatures. So if you have a warm object and a cooler object that are in contact with each other, it's heat that flows from the warm to the cool, always in that direction, and it'll do that until the temperatures of the two objects are the same. Now, heat is energy, as I said here, so therefore it's very proper to use the units of joules for heat. We learned that joules is a unit of work or energy in previous chapters. Another unit of heat that's pretty common, especially in the U.S., is the calorie. And we'll talk more about that on the next slide. Internal energy is defined as the total of all energies within a substance. So this could include the kinetic energy of the molecules that we were just talking about, and it could also include the potential energy, which is reflected in the state of the object, solid, liquid, or gas. And we'll talk more about that in the next chapter. Now, when heat is given off by a substance, the internal energy decreases. So that's either shown as a drop in temperature of the substance or by a change in state of the substance. Now, we spoke a little bit in the previous slide about heat and the units of heat, and we mentioned that joules and calories were appropriate units of heat. Let's just talk about the calorie here for a minute. The calorie is defined as the amount of heat needed to raise 1 gram of water 1 degree Celsius. And there's more about that in the book. Now, different materials have different specific heat capacities. So, for example, if you have two different substances and you have the same mass, you have two blocks of metals, for example, that are the same mass, and you allow them to soak up the same amount of heat, the temperatures will go up by different amounts. And that's due to this property of the substance that's called specific heat capacity, or just specific heat is what it's usually called. Now, water has a high specific heat, one of the highest specific heats of all the substances. So that means it takes an awful lot of heat to raise the temperature of water, or by the same token, when the water is cooling off, it can give off a whole lot of heat and its temperature does not drop by that much. And this has a dramatic influence on climate because we know that coastal regions tend to be warmer during the winter, and that's because cool air is warmed by the oceans, which have not only a high specific heat but a whole lot of mass. And by the same token, in the summertime, their coastal regions tend to be cooler because they absorb the heat. Another property of increasing temperature is thermal expansion. So when you heat something up, we already said that the temperature goes up and the average kinetic energy of the molecules increase, which means that they are moving faster and they tend to expand. Now, we see this in bridges. For example, they have what they call expansion joints, so that in the summertime, when the temperature goes up, the bridge doesn't buckle. Thermostats have a bimetallic strip, two different metals that have two different expansions, and when they heat up, the metallic strip tends to bend, and you can use that as a thermostat in order to make contact and break contact of a little circuit that controls a furnace when the temperature changes. Okay, so we've said that substances tend to expand when the temperature goes up, and of course that would mean that when the temperature goes down, they contract. Now, water is a little bit different in that if you were to take water at, let's say, room temperature and decrease the temperature, like most substances, as you decrease the temperature, the volume of the water would decrease. And so in other words, it would be contracting. However, it'll do this up until 4 degrees Celsius. From 4 degrees Celsius until 0, when it finally freezes, it actually expands. So the volume of water is going to decrease until it reaches 4 degrees Celsius, and then as it is cooled further from 4 to 0, the volume tends to expand. So at 4 degrees Celsius, water tends to be the most dense. Now, furthermore, when it finally does freeze, it expands further, which is again pretty unusual. So that's why, for example, ice floats in water because it's less dense. And this has got some dramatic effects on our lives. For example, lakes, take for example Lake Champlain, they hardly ever, Lake Champlain never freezes solid. And that's because when the lake starts to freeze and ice does start to form, it tends to float on the top. And when it does that, eventually it'll freeze over at the top, but then it's going to insulate the water that comes down beneath it. So as it gets colder, the thickness of the ice does increase, but it never gets beyond a foot or 18 inches in depth. Car antifreeze is another way that this expansion of water impacts our lives. If we didn't use antifreeze on our car, we use water to cool the engine. So when it gets down to below freezing, that water would expand, and as it freezes, and as it does that, it could actually or would actually crack the engine block, which would be certainly a bad thing for your car. So in order to prevent that from happening, we use antifreeze in the water that cools our car, and so that prevents that water from freezing.